Hi, everybody. Welcome back. This is Miss Wiesen, and this is the second podcast of Unit 2 AP Chemistry. And we're at the top of page 5. And in today's podcast, we're going to focus on ionic bonding and structure. Now, if you can remember earlier in the unit, we learned that ionic bonds are going to form between a positively charged ion and a negatively charged ion. And when they get close together, that force of attraction between the two is so strong that they're going to be held very closely together. And so the final result of the solid that forms with an ionic compound is in the formation of something we call a crystal lattice. And let's go ahead and use lithium and fluorine just to highlight what crystalline lattice means and even how they form. So lithium in its neutral state is going to form a +1 to become stable, and fluorine is going to turn into a fluoride ion and form a -1. And when these two ions come close together, the formation is going to be held through their valence electrons, because remember, when we talk about bonding, it's the bonding and the attraction of the valence electrons of the elements. And so this connection that lithium and fluorine hold are ultimately going to create a lattice. You can see here that there shows two kind of different representations of a lattice formation between lithium and fluorine. And for an ionic crystalline lattice, for it to form, it actually goes through many energetic states. Okay, and so naturally the bonding here can be described by Coulomb's law, which at this point you've heard numerous times. And what we have here is the packed version on the left. We call this the packed version. And the image on the right, we call the expanded version. Either way, it's appropriate to say lattice energy instead of bond energy when we're talking about ionic crystalline structures. So I'm going to jot that down to the side so you can actually remember to start using the correct language. So you might want to add this to your notes. So we say lattice energy instead of bond energy. Now, before we move on, let's take a look at the image over here on the left. I just circled it. It looks a little confusing, but these essentially are the various steps that lithium and fluorine will undergo to ultimately form their lattice structure. You can clearly see that this process is not a one and done scenario. In fact, it involves many different exchanges of energy and conversions of elements into different states. Notice, however, that if you take a look here in the very last step, the energy value is negative. So if you kind of want to label your diagram, this is actually where this diagram starts. So initially, you would take solid lithium and diatomic fluorine. Energy is added into the system, and ultimately in between step 1 and step 2, you are actually taking lithium in its solid state and you're turning it and converting it into a gas. In step 3, in step 3, you're actually going to ionize lithium. In step 4, you're going to create elemental fluorine. And now we're at step 5. And notice our energy values now are negative. Remember why that's so. Remember, negative values indicate that the elements bonding together are actually more favorable and more stable than if they were by themselves. But take a look. Look at this big, huge energy, negative energy value to get to step 6, which is actually when we finally arrive at our solid ionic compound. And remember, it's going to form that crystalline lattice structure. And the bonds between those ions are referred to as lattice energy. Let's recap Coulomb's law. I guess third time's a charm here. And the reason why we bring up Coulomb's law here in ionic bonding is because we can actually use Coulomb's law to help explain ionic bonding. So again, the formula's over here, you guys. I think it moved. I wanted it to be more over here, but it's all the way over here to the right. Remind yourselves what Q1 and Q2 mean. In the case of ionic bonding, Q1 would be the charge of the positive ion, and Q2 could be the charge of the negative ion, where R, remember, is the distance between the two ion centers. And then, of course, we got Coulomb's constant K in there. Now, the attraction of ions depends directly on the magnitude or size of the charges and is inversely proportional to the distance between them. So again, one more time, let's say it. Lattice energy is synonymous with bond energy. So when you hear that word, that's what's being referred to here. Okay, let's try exercise 5 and put some of this into perspective and application. It's asking which substance will have a higher or stronger lattice energy, lithium fluoride or potassium fluoride. And then there's sodium fluoride versus sodium bromide. Use Coulomb's law to explain. And I know that I've put words here and gave you the answer, but let's talk about this. I have over here the periodic table, and in the question, it was asking us to compare lithium fluoride to potassium fluoride. That was for the first one. Now, before we go on, it's clear here that our metals are different, but the non-metal fluorine is the same. So quickly, I'm going to look at lithium and potassium. I noticed that on the periodic table, they belong to the same group. So lithium is element 3, go down a couple more, there's potassium. Now, both of these are bound to fluorine. So what we really need to look at here is what is the difference between lithium and potassium? Which one would technically have a stronger lattice energy? Well, if you look here, potassium, element number 19, is actually going to be bigger. It's going to have more orbitals, and so the actual atom itself is going to be larger. And because it's larger, it's going to have a larger radius. What does that mean about force when it comes to Coulomb's law? And if you compare that with lithium, a smaller atom, where those valence electrons and that positive nucleus are closer together. So what do you think is going to happen here? Which of these elements, lithium fluoride or potassium fluoride, do you think would have a stronger lattice energy? Now, if you said that it's lithium fluoride, then you're right. And that is because potassium is bigger. And since potassium has a bigger, or is larger rather, those valence electrons are further away, making the force weaker, making the force of attraction weaker. So in the first example here, lithium fluoride would have the strongest lattice energy. Now, what about sodium fluoride and sodium bromide? And let me go ahead and write those here. In this particular case, we have the same metal, but our nonmetals are different. So one was fluorine and the other was bromine. Again, if you're kind of thinking off the bat that this would kind of relate to the first example, where we have fluorine and bromine in the same group, and bromine is a larger element because it's element 35 compared to fluorine, which is element 9. And since bromine is larger, its force of attraction is going to be weaker, and therefore its lattice energy is going to be weaker. So if you said sodium fluoride has the stronger lattice energy, then you're right. Let's do exercise 6, which looks like we're doing some more on crystal lattice structures. It's asking which of the following images would correctly represent the lattice of a potassium fluoride. All right, well, we know potassium fluoride is an ionic compound because potassium is a metal and fluorine or fluoride is a nonmetal. Let's talk about the options that would not correctly represent the lattice structure of potassium fluoride. Take a look at A. Quickly, you see here that charges are clustering in groups of 4. And would it make sense that this would never likely happen because those clustered charges are so close to each other that they would ultimately serve to repel? So if I had a cluster of these 4 negative charges, I can say that there would be repulsion, the negative charges within that cluster. And so this would never happen. If you look at option C, kind of the same reason. And although it's alternating rows of positive and negative charges, what you see here is that within any given one row, there's too many like charges within that area that would likely, again, cause a repulsive effect, and therefore that structure would never form. If you go over to option D, it seems like those ions are just simply too far from each other to actually have an attractive force. So if you take a look at B, which is actually the answer, This one would correctly represent the structure of potassium chloride. And so therefore, at the end of the day, we will alternate positive and negative charge to reduce the repulsive forces and to optimize the attractive forces. Moving on, earlier in the unit, we talked about substances that form metallic bonds. Okay. And truth be told, that these substances are strictly made of metals, but they don't form a bond per se. Okay, that was a little bit misleading. All right, so instead, let's take a look at what's actually happening here. Take a look at the example of the electron C model. There is a typo here. The electron C model, it's supposed to say of a pure metal, okay? Not magnesium. I apologize. All right, in this particular case, this structure looks like it's simply an array of positively charged ions that are surrounded by delocalized valence electrons. Okay, in other words, if you look at these electrons, when you say the word delocalized, that basically means that they're not bound to any one area, that they're kind of floating about. And you can kind of see where they got the name for a pure metal. It's called the electron C model, where, again, electrons are shared equally among the atoms, and the structure is based on simple, close-packed structure that contains no fixed directional bonds. So there's actually no bonds per se in samples containing pure metals. What about an alloy? Probably heard of an alloy before, and they're very common in society. In fact, most of the metals that we work with to build or to manufacture in industry are made of alloys. You've probably heard of brass, cast iron, steel, solder. These types of things are examples of alloys. And simply put, alloys are simply combining two or more metals in a different kind of ratio or format. So we have two different types of alloys. We have substitutional alloys and we have interstitial alloys. And if you take a look at this first example on the left, the substitutional alloy, we can just say an example could be like brass. Okay, brass is an example of a substitutional alloy. And brass is actually made up of copper and zinc. Why don't you pause me for a second and take a look at where copper and zinc are on the periodic table? You should have noticed that copper and zinc are on the same period right next to each other. They have very similar sizes, okay? And you can see here that a substitutional alloy, are metal atoms that are kind of replaced occasionally by another type of metal atom that's similar in size. In fact, the word substitutional simply means to replace. And that's why it's called a substitutional alloy. You might have also heard of pewter. That's a substitutional alloy. Maybe sterling silver you've heard of. That's also a substitutional alloy. Okay. If you actually take a look at the image on the right, this is the second type of alloy, and it's called an interstitial alloy. And an example would be steel, for example. And if you happen to look at where carbon and iron are found on the periodic table, you would quickly see that they're nowhere near each other and they have varying sizes. And in this type of an array of metals, you're going to have smaller metals fill the spaces between the larger metals, okay? And again, the word interstitial means between. Really quick, let's just go ahead and do a quick recap. In the space below, describe what you believe to be the differences of these two types of alloys. So I'm going to go ahead and jot some notes down. How about you pause this video and write a couple of the things that you gleaned in the last couple of minutes about alloys. Welcome back. I jotted some notes down. Go ahead and check yours with mine. Again, I just recapped what we just talked about. So both types of alloys contain only metals. One type of alloy, the substitutional one, simply replaces or substitutes one metal for another with similar size. And the other, an interstitial alloy, adds smaller metals to the existing array of metals, more specifically in the interstices. All right, let's do example or exercise number 7 in our notes. It says, in order to make gold stronger and harder, It's often alloyed with other metals such as copper and silver. Consider the two alloys. One is of gold and copper, and the other is of gold and silver, each with the same mole fraction of gold. Remember, mole fraction is the ratio of moles present of gold to the total number moles present. If the gold copper alloy is harder than the silver gold alloy, propose an explanation based on the information in the table below. Okay, before we jump into this, I wanted to just bring a note here. It was telling you that about the mole fraction of gold, so the ratio of gold to the ratio of everything present in that alloy. You know, when we talk about mole fraction, we can also kind of relate it to things you've already learned about, like percent abundance or percent composition or percent error. A lot of times in chemistry, when you hear the word mole fraction or these percents, you're almost always going to take a portion of the thing you're interested in, dividing it by the whole. So mole fraction is no different. Okay, let's go ahead and take a look here. I have the three elements: gold, copper, and silver. I see their metallic radius, I see their melting points and their oxidation states. And it is asking me, again, let me highlight the question. If, so it says the gold copper alloy is harder, propose an explanation why. Okay, alrighty, so right off the bat, I'm gonna go to metallic radius. And I notice that the silver, and I'm gonna just make a bracket, and the gold have comparable, identical metallic radius. Would this be a substitutional alloy, or would that be an interstitial alloy between gold and silver? And how do you know? Well, since gold and silver have the same radius, substitutional alloys are going to take atoms of the similar size or metals of the similar size. So we would know that the silver gold alloy would create a substitutional alloy. And then if you take a look at the radius of the gold to copper alloy, they're obviously not the same. They're different, copper being smaller. So I would assume that the copper gold alloy would be the interstitial alloy. Okay. And so what this leads me to believe is that since copper atoms are smaller than the silver atoms, and since those copper atoms are in the interstitial spaces between the metals, I'm going to argue that the copper gold alloy is going to be stronger because the copper atoms in the interstitial spaces of the alloy are going to make that metal even harder. It's going to be harder to displace or move that metal because of those copper atoms wedged into the spaces in between. Okay. All right, you guys, that was it for ionic bonding. Thank you so much. Let me know if you have any questions.